Okay, so today I'm going to talk about why not to be afraid of priors too much. So this is the first time I'm giving this talk. So some of you may end up, being more afraid of priors afterwards. I haven't tested it, so let's see. Okay. So because this is the first talk of today, I'm going to, very briefly go into some very basics of Bayesian statistics. And so what is a prior, basically? And the prior is one part of two main, important parts of Bayesian statistics, basically. So what we call, okay, so that was wrong. I know what buttons not to click. That button actually. Yeah. Okay. So priors, or at least how I would define it, as a probability a distribution of an unknown quantity, so something we want to learn about. And there is the likelihood, which is a probability distribution of some known quantities. So the known quantities we usually call data, and the unknown quantities we call parameters, right? But we more generally you can just speak about known and unknown quantities. And so what we're going to do in Bayesian statistics is we have a model. Sorry. It's super automatic. So what do I click here to make it large again? Sorry? This one? Oh, okay. So very nice. I'm not a Mac user. So we have a model M, and we want to estimate the parameters of the model, which we call theta, and there's the data D, or the unknown quantities. And so the posterior distribution, which is the probability distribution of the parameters after having seen the data, and also after having specified a certain model consisting of likelihoods and priors, is the product of the likelihood of this model, so the distribution of the data given the parameters times the prior, so the distribution of the parameters before having seen the data. I'm writing M after the dash for every of the probability distributions to make clear that every model has its own prior, has its own likelihood, and thus its own posterior distribution. So we are always going to talk about the posterior distribution of a certain model. So if that confuses you, just ignore the M. So I'm just trying not to use the presenter. Okay, so now people are often afraid of priors because we give information about the parameters into the model which are not coming from the data, right? So that's basically the definition of the prior, and there are some thoughts of people which you can understand. So first of all, people have learned or say that priors are inherently subjective. So every researcher, every whoever wants to do Bayesian statistics can have its own prior. So they're subjective in a sense. That's what people say, and I will talk about this. And then there are others saying that priors bias your analysis. So I want to talk about what bias is, and how priors may end up biasing or not biasing analysis. And then the third one is all of the most, which is you should let the data speak for themselves, right? The people that tell me this sentence are usually the ones who are very confident about their own knowledge about statistics, but by saying this they are proving being ignorant basically to statistics. But anyway, so I like this. I don't think that I will have enough time to speak about the third one actually. At least I haven't prepared some slides. Great. And then there's the classical pragmatist statistics who don't use prior, so they're just using the likelihood, at least that's what they think. So they say classical statistics is fine without priors, we just have the likelihood, that's enough. And then there are many people, and at some point myself as well, who say I have no idea how to set appropriate priors, and that's certainly something I can understand. I often don't know myself how I can set appropriate priors. So that the second part of the talk will be about how to set, or giving you some ideas to set priors. I'm not going to talk about how to actually set appropriate priors because that's a very very large topic, and I would have to go in specific models, and I'm just trying to give a general talk. Okay, so the question is, are priors inherently subjective? And the answer is, they can be. So for instance, these are two different priors. So on the left, we have some prior, effect size, standardized effect size. It's Cohen's-d for those who know this. And the prior says, okay, before having seen the data, I'm pretty sure the effect size is pretty much 0, so the drug is not effective, the therapy treatment is not effective, whatever the motivational training for some employee is not effective, and I'm somewhat uncertain about how effective it is. So it could have a positive effect, it could have a negative effect. So, but on average, I believe there's no effect of the training. And there's the other guy, on the right, who's pretty confident that the training or treatment or whatever will be rather effective. So he or she sets a very informative prior, telling us he believes or she believes rather strongly in the effect. So both may be sort of right with their assumptions, and they may base their the prior on different information. So in a way, priors are subjective because people have other opinions, but also other knowledge. So depending on the knowledge, the prior might change. So in a way, we can say yes, priors are inherently subjective, or are subjective, or can be subjective. But there is also much other information which we can put into priors which isn't necessarily subjective. For instance, if we have seen some experiments before for this drug or for this antibiotic, and we know it works for this particular bacteria, for instance, then we base our prior on what we have seen before in previous experiments, and if these experiments were reasonable, possibly the prior is not necessarily subjective. It's because you base it on previous reasonable scientific knowledge. And sometimes we don't really want to incorporate explicitly prior information, like in the case on the right side, but so we just know the scale of the effect. So assume that's not Cohen's-d, but it's just the difference in height of women and men, in meters or in centimeters, right? So depending on the scale of the effect, we know what is likely. So it's unlikely that the difference in size is like 10 meters. That's pretty unlikely, right? But more likely it's like on average 10 centimeters or whatever. So just based on the knowledge of our scale, right, we can set appropriate priors because based on common sense we know how large an effect can be or can't be. Yeah. And there are other situations which I will talk about later on, where we just want to regularize our model, making it less excited about extreme values, and making it less likely to fit on noise. Yeah? So those are situations where we use priors, but not necessarily to put in subjective information, but just to make our model do better predictions and actually make better estimates, not just to explicitly incorporate subjective sort of prior knowledge. So priors may be subjective, but not necessarily, at least from my perspective. But in any case, and that's why we're using them, the priors influence the posterior. So that's of course clear because of Bayes' theorem. But it's of course important to note that if we use different priors, the posteriors will differ as well. So those are the two posteriors for those two priors. For 100 simulated observations with a true Cohen's-d of 0.5. So we see that because we put much information on the bluish prior, the posterior is sort of more on the right because we put more prior information. So that's just nature of Bayes' theorem, and it's just important to know that what we do with priors, we influence the posterior. And how much we influence the posterior depends on how strong the prior is, but also on how much data we have. So if we have few data, like 100, the influence of in this case, very informative, right, and posterior will be large. But as soon as we get more data as compared to the complexity of our model, the effect of our prior will vanish. So if we have infinite amount of data as compared to the number of parameters, then we have basically no effect of the prior anymore. So we talk about the prior as a higher order effect. So it's less inferential than the data once we gather enough data. And so of course, usually we don't set such a prior as on the right-hand side unless we have some very strong prior information. So usually between two priors, the posterior may not vary that much. So we use the prior to put in certain information, and if we want to find out how the prior changes the posterior, we should use different priors and see different reasonable priors and see how the posterior changes. We call that sensitivity analysis. And no matter what prior we use, we should always report it. So even if we put in subjective information, or in particular if we put in subjective information, we should or we have to report the prior, to make sure people can criticize our prior. So it's only a problem if we are reporting the posterior without reporting the prior. So people don't know if we put in accidentally maybe an informative prior into the model. Yeah, so always report your priors along with the posteriors, so that people understand what you do put into our model, so that you can be criticized basically not only for the likelihood you're using but also for your priors. And then even if your prior is subjective, people can criticize you for it. So that's how scientific progress really works. Okay, so the next point is do priors bias your analysis. So first of all, what's the definition of a bias? So an estimator theta hat of the parameter theta is called unbiased, so not biased, if the expected value of our estimator is equal to the true parameter. Right? So on average, the estimator is right. Then we call an estimator unbiased. And that's nice, right? So if there is truly a true parameter, we want to be on average right. Yeah? So that's an understandable criterion of an estimator, be it a classical estimator or a Bayesian estimator. And there are some informal corollaries which I wrote down here. So if an estimator theta hat is unbiased for a given prior, whatever this prior is, it will likely be biased for most other priors. So if it's unbiased, let's say, just making something up, for left-hand prior, it likely will be biased on the right-hand, for the right prior, because we shifted it. Yeah? So in a way, priors will bias your analysis, because if you change, your prior, this unbiasedness might go away if it was there before. Yeah? So in a way, again, this is right. Priors may bias your analysis. But what I want to show you briefly is that biasness or unbiasedness is fragile anyway from different perspectives. For instance, if we have an unbiased estimator at a given scale, and we transform this estimator using some nonlinear transformation, for instance, exponential transformation, call it f, then we know pretty surely that the expected value of the transformed estimator will no longer be the transformed value of the parameter. So if the estimator is unbiased on a given scale after nonlinear transformation, likely it won't be unbiased anymore. So unbiasedness is a quite fragile concept, even though frequentists like it that much. For instance, if we have a variance parameter and we want to estimate sort of the true variance in a population, then we know that our usual variance estimator is unbiased for the population level variance. But as soon as we transform it, for instance, using a square root to get to the standard deviation, the classical standard deviation is no longer unbiased, at least for small sample sizes, for the true standard deviation in the population. You assume something to happen. So unbiasedness is rather fragile concept. And also in classical statistics, it usually only holds in the limit, so for basically infinite amount of data or very large data sets. And basically the same holds for Bayesian statistics as well, because the influence of a prior diminishes for larger data. if you're interested in unbiasedness, we can try to estimate the true model with as much data as we like. Then we will end up with unbiased estimators. So the problem of biasness or unbiasedness is there are also classical statistics. It might even be larger because for very small data sets and rather complex models as compared to the size of the data, the model, or the data doesn't contain enough information to reasonably inform the parameters to yield something which is reasonably close to some reasonable estimate or some unbiased estimator. So by using explicit prior information in particular, then when we have small data and rather complex models, we can actually make our estimates more unbiased by using Bayesian statistics, even though Bayesian statistics is usually not primarily interested in biasness. So we can beat frequentist statistics in their own game, right? By using priors, especially when we have if we have few data. So priors do bias your analysis at some point, but sometimes or usually it's not necessarily about bias, but because getting reasonable estimates which may be reasonably close to some idea of the truth. And Bayesian statistics can actually help us getting there by providing information to the model which isn't in the data, but we should still use. Yeah, so don't be obsessed with some sort of unbiasedness. This is not the concept you should be striving for in all cases. Okay. Okay. So now to the fourth point on my list, which was that classical statistics doesn't need priors. And what I want to talk about now is that I think, also from my perspective, from a Bayesian perspective, priors are unavoidable. So that's model one. Model one was the one on the left-hand side, so the red curve. So we had some data y, and so the data was normally distributed with some mean parameter d, so we wanted to estimate d. In this case, a known standard deviation of 1. And so we put a normal 0, 0.5, 0.7 prior on d, saying that we expect a priori that the mean of the d is 0 with a standard deviation of 0.7. And then there was model 2, same likelihood, so the first line is the likelihood, and the second part is the prior, saying that we expect on average an effect of 5 with a standard deviation of 0.5. So this was the right prior. Okay, so now we have the third model, which we could call the fragmentist model, just having the likelihood. Y is distributed normally around d with a fixed standard deviation of 1, and no prior. So the question to you would be, is the third model really free of priors? So what do you think?
No.
No, nice. That's what the title says. Right. Okay. So the idea is that from a fragmentist perspective, we don't have a concept for a prior, so we like to think that we are not using priors. But once we are going Bayesian, we understand that fragmentist statistics is just a special case, sort of, or fragmentist estimates are just a special case of Bayesian estimates, in the sense that we're using flat priors. So every parameter value is equally likely a priori. And so the posterior mode, so the highest value of the density, has a point estimate. So from this perspective, from Bayesian perspective, the third model has a prior, which is completely flat. So all values are equally likely a priori. This is usually pretty unlikely. For instance, in psychology, we know that Cohen's d will usually be roughly between -1 and 1. So a Cohen's d of 10 is super unlikely, or 1,000 is super unlikely. Or that the average size of women and men differs by like 1 kilometer. It's pretty unlikely, right? But from a fragmentist statistics, a priori, everything is equally likely. So I used to talk, and I continue to talk about those sort of priors as uninformative, in a way that they're not putting much information into our model, but in a way they're pretty informative, in the sense that we put infinitely much probability to very unlikely values. So 2 kilometers size difference, right? Or 3 kilometers. So in a way, we definitely use priors, even though we don't talk about them in fragmented statistics, and those priors even end up being sort of informative in the way that we're putting much probability into values, which are, of course, by common sense, unlikely. So priors are, from a Bayesian perspective, unavoidable. We just don't see them in classical statistics, but they're still there. And priors also appear in some unexpected places. So this is the basic multi-level model. Annotations. So think of it as a just standard classical multi-level model, fragmentist multi-level model. We have some data y, which is distributed normally around some intercept b0, but this intercept is not common across all observations, but it's depending on, say, the person's j, so it's the person index. And then we have some effect of a predictor x, and the effect is quantified by our parameter p1. So think of it as y being the outcome of a therapy, or outcome of a session of a therapy, and x being the motivation of the patient. So because we have, like, for instance, longitudinal data, so multi-sessions per person, we have multiple observations per person, so we have to account for this dependency between those multiple observations per person. And we do that, for instance, using a multi-level model, in this case a varying intercept, so we say the baseline effectiveness of the treatment, so of y, will differ across persons. Some persons will benefit more, others will benefit less. Yeah? And I'm ignoring the other parameters right now. So then what we do in a classical multi-level model is we put sort of a distribution over the variant intercept. So we say that the variant intercepts B0J are normally distributed around some average common intercept B0 with a standard deviation SD0. And along with B0, we will be estimating B0 and SD0. So we have sort of multiple, hierarchy of parameters in the sense that we say, okay, look, every person has its own intercept, but they're varying across one common intercept with some standard deviation, which will be estimated. So this is the fragmentist multi-level model, no Bayesian involved. So the question is, I understand nobody's talking to me right now. So is this the second line? Is it the likelihood? Is it the prior? Is it something else? I think Ladislas could. He could answer this question because we were writing a paper together, and there was one reviewer telling us that we should separate the model from the prior. We were explaining that the prior is part of the model. And he was also saying that we should separate the random effects distributions, whatever there is, from the prior. So because apparently the reviewer was fragmentist and didn't realize that what classical statistics call random effects distribution is in a Bayesian framework just a prior, because those B0Js are parameters. So a distribution of a parameter is a prior. Yeah. So Bayesian classical statisticians are using priors as well. They just don't name them priors. They talk about random effects distributions or varying effects distributions, or they don't talk about them at all. So, but they're still using it. So they're using priors and benefit from the what Bayesian statistics can offer them, but they're doing it in a very weird way, right? By omitting Bayesian terms and omitting Bayesian statistics and doing it in another complex way, but still they're using actually what is a Bayesian concept. And it becomes clear once you're a Bayesian statistician to see that this is just a prior with some hyperparameters. So this is a parameter with a prior, and there are other parameters. So in this prior, and those parameters in turn can have priors, right? So, I haven't written them down, but they can have. So a random effects distribution is just a prior in a Bayesian frame. Then there's another example where priors can appear in unexpected places. For instance, consider model 1. So assume it's just the same as the last one, but without multi-level structure, so just one outcome per person. So for instance, one treatment effect, depending on the motivation X of the patient. And what we usually do in psychology is, or we tend to ignore measurement error. So the treatment effect Y, or the treatment outcome might be measured with error because it's just a questionnaire. So patients fill in, and we have measurement error. So we can incorporate this measurement error into our model by understanding the reliability of the questionnaire and specifying what I here call SDY, so sort of the uncertainty, the measurement uncertainty. So in the first model, just basic one. In the second one, we say, look, we now acknowledge that Y is actually measured. So Y measured is now our data, and it's normally distributed around some assumed true, latent effect Y for each person with some known uncertainty around this measurement. And then we say, okay, look, Y is now our latent true treatment effect, and this is in turn, estimated using, the same model we used above. So right now, in the first model, the first line was clearly a likelihood, because Y was data. But now, because we have put some measurement equation into it, now Y is suddenly a latent variable. A latent variable is nothing else than an unknown quantity, a parameter. So suddenly, what was a likelihood before becomes a prior, because it's an unknown quantity. Right? So Bayesians are not, surprised. So it's just a distribution over some quantity, whether it's unknown or known doesn't really matter. We just have to have enough knowns to identify the unknown. But we cannot really express the second model consistently in a fragmentist framework, because then we end up using priors even though we don't have the concept of priors. So priors appear in unexpected places, also in fragmented statistics. The same applies to all structural equation modeling, where we will be using latent variables. As soon as we put sort of an assumption over a latent variable, this latent variable is because it's unknown, so the assumption of the distribution becomes a prior. So we are actually using priors all the time in classical statistics, but we don't call them priors. So in the first model, the first line was a likelihood, and the second model, the second line, was actually a prior, depending on whether we measured or we used measurement error or not. Okay, so the second part of my talk will be how do I set appropriate priors? And I'm not going to answer that. Because, so jumping to the conclusion, setting reasonable priors is hard in any case. But there are some things we should think about when setting priors. So the first thing is that we should think about what's the goal of my analysis, what's the goal of my prior. So for instance, I could explicitly incorporate explicit prior knowledge into my model, for instance, based on previous experiments. Or what I usually do in multi-level models, I make my estimates less excited about extremes. So I'm providing shrinkage, I'm preventing from overfitting, I'm preventing the model from fitting noise. So just, doing bad stuff really by using reasonable priors. In some cases, I use the prior, I have to use a prior to identify my model, because some parameters are or cannot be identified, so informed by the data to a reasonable amount. So I have to use a prior. What fragmented statisticians usually do is they just fix the parameter, which is much more informative than putting a prior on it. But if nobody is, really cares about fixing some parameter in a structural equation model, if the model doesn't converge, they don't really care, but they should. And there's a better way to, identify a parameter using a prior as compared to fixing it, because we still have enough uncertainty, or we still have uncertainty in the parameter, so we can really estimate it based on, or with the help of the prior. And then there's some third goal, when we want to using base factors for hypothesis testing in Bayesian framework, we definitely and always have to think of our priors, and our priors should always depend on the goals of those priors. So there's no general prior which we can just throw at a model and it works, but our prior will have to depend on our goal. And in any case, setting reasonable priors is hard. We can always go for very, very wide priors. That's what I'm, for instance, using in BRMS. So that is at least something that will usually work in most of the cases, but it's not ideal, because usually we have prior information. Usually we want, prevent our model from overfitting and stuff like that. So usually we will be wanting to use priors, But to make something very general in a software package, usually the priors are pretty wide so that we don't mess up something accidentally. Okay, so here's an example of how to incorporate explicit prior knowledge. So first goal. Suppose we want to estimate the speed of light. Right, and we have a previous experiment has found c, so the speed of light, to be roughly 3 million meters per second or 300,000 kilometers per second. And the estimate of the previous experiment was with some uncertainty, and the uncertainty in measures of standard deviation, say, is 2 meters per second. So we're pretty close already, but we are not yet there to an exact estimate of the speed of light. And the question is, how do we incorporate this prior information? We just use an informative prior. So we now gather our own data, which we call y, and so we can update this prior knowledge based on the previous experiment by means of our own data y and see how our own data improves the estimate which was already there in the literature. So we say our data, let's say, is normally distributed, so that's our data is some multiple estimates of the speed of light. So normally distributed around the true speed of light, a parameter with some standard deviation sigma, which we are also going to be estimating. And we put an informative prior on C based on the previous experiment. We were having like close to 300,000 kilometers per second and with the uncertainty of 2. So by doing this, we update the existing knowledge about the speed of light by means of our own data. So others have gathered data and we combine them with our own data and form a new estimate which is informed by both the old and the new data. So we're using the posterior of the experiment before, suppose this was a posterior, as the prior of our own model. So we're doing sort of model updating. Right? So in this case, we're incorporating explicit prior knowledge. I wouldn't call this subjective, right? Because it's based on reasonable scientific literature, hopefully. But this is a way to incorporate explicit prior knowledge based on formal studies. So then there's the idea which is most important to me. Usually when using priors is make your estimates less excited about extremes. We could also say make it less prone to overfitting, so to fitting noise, to fitting signal which isn't actually there. Yeah? And we do that usually using multi-level models. So we have the first two lines, which are basically the varying intercept multi-level models, which I was talking about a few minutes ago. And then I want extreme values of B0 to be shrunken towards the mean, right? Because I don't believe very extreme values likely there in part because of noise. So I want to make them more conservative. I want to shrink them to the average value of some bit to the average value. And I can do that, for instance, just by using multi-level models, and then additionally by setting somewhat informative priors on the hyperparameters. So in this case, on the varying effect standard deviation, SD0. So if this SD0 is a priori small, extreme values will be a priori unlikely. So people having, showing very extreme responses to the treatment effect will have estimates shrunken more towards the mean. And that's a good thing, because usually it improves our average estimates. For instance, it improves the estimate of B0. It improves predictions based on our model, usually. And it, generally makes our model, less excited about unrealistic patterns in the data, less excited about extremes, and less prone to overfit. And this mechanism of setting hierarchical priors on parameters provides shrinkage, so shrinking rather unrealistic or extreme values towards the mean of the values to make them more conservative, to make them, in a way, more reasonable. And this is one of the main purposes of multi-level models. So we do that all the time because we want, right? We want shrinkage, we want more conservative estimates, more reasonable estimates. And we want that as well in the classical statistics. So that's why we will be using multi-level models in Bayesian and classical statistics as well. But we can, improve the shrinkage, if we like, by setting informative priors on the hyperparameters. And then there are situations where we want to identify our model. So for instance, if we have some outliers in our data, we know that when we are performing linear regression, those outliers can strongly influence our regression line. Yeah? So sometimes we will exclude the outliers because they're just plain wrong data, but sometimes they're reasonable data, but their influence on the regression line is unreasonably large. So what we can do is, at least in the Bayesian framework, we can assume instead of a normal distribution of our response variable, we can assume a t-distribution, which has just somewhat wider tails. So it's more likely under the t-distribution that there are some extreme values happening. In the normal distribution, it's unlikely. So as soon as there's an extreme value, the normal distribution says, okay, that's unlikely, so I have to go somewhat there to the extreme value to make it reasonable. But the student t-distribution doesn't care, it just makes its tails wider so that, the one outlier doesn't affect my regression line, for instance, too much. So this is what I sometimes call robust linear regression. Robust linear regression has many meanings. In this case, for me, it means using a t-distribution instead of a normal distribution as my response distribution. So there's some plots about the normal distribution and some different values of the t-distribution, depending on the so-called degrees of freedom parameter, df. No? So for small degrees of freedom in the extremes of 1 degrees of freedom, the tails will be rather wide. They will be so wide, it's for those with mathematical background, the mean doesn't even exist for this so-called Cauchy distribution, t-distribution with 1 degrees of freedom. But as soon as we are, getting up higher with the degrees of freedom, for instance, 25 degrees of freedom or 50 degrees of freedom, the t-distribution starts to converge to the normal distribution and is virtually undistinguishable from the normal distribution. Right? So if the data tells me the response is really normally distributed, the student t-distribution can incorporate that knowledge. But if the data tells me there are some outliers, the t-distribution will get wider, should be less influenced by outliers. The problem is, with this df, degrees of freedom parameter, it's in certain situations not identified by the model. So for instance, if the data is really consistent with some normal model, then we cannot distinguish between 50 degrees of freedom or 100 degrees of freedom or 1,000 degrees of freedom, but because everything is basically just very close to the normal distribution. So we have to put a prior on the degrees of freedom so that they become identified, so that we can estimate them, even if the degrees of freedom end up pretty large because the data is close to a normal distribution. So there's a sort of default prior for degrees of freedom. It's a gamma prior with shape 1 of 2 and shape 2 of 0.1. Someone came up with it. It works pretty nicely. So that's the prior of the degrees of freedom, and it makes sure that even if the data is consistent with a normal distribution, we can still estimate the model. Yeah? And but if the data is not consistent with the normal distribution, so we have small degrees of freedom, the prior still allows us to have small degrees of freedom. Yeah? So that way we can really estimate robust linear regression using a t-distribution, which usually doesn't work in a frequentist framework because df tends to make problems. And there's how much time do I have left?
So 5 minutes.
5 minutes, perfect. Okay, so then there's another situation where we have to use priors, which is when we want to use base factors. So base factors is one way of comparing two models in a Bayesian framework. It's not the only way, but it's a very common way nowadays. I'm not actually sure if I like them so much. But let's say we have two models, M1 and M2, then the base factor is some sort of complex integral, or what is basically just the likelihood of the first model times the prior of the first model integrated over the whole parameters, and the same for the second model. So we call this integral using the marginal likelihood or evidence of a model. So it's the probability of the data after having averaged out the parameters, or more precisely, the sort of probability of the data given the model. So we are comparing the probability of the data given the model given the first model as compared to the probability of the data given the second model, roughly speaking. And in the first equation, we already see that the base factor will likely depend on the prior, because the prior goes into the integral. But that's nothing special because we know the posterior distribution is influenced by price as well. But when we sort of rewrite this base factor for a very specific case, we see that usually base factors end up being much more affected by price than just the posterior distribution. So for instance, if our first model says our theta, so we have just one parameter of interest, is equal to some certain value theta 0, let's say it's 0. In the treatment case, we can say model 1 assumes that there is no treatment effect, while the alternative model 2, assumes that there is some treatment effect, so be it negative or positive. Okay? So it's reasonable, to ask the question, is the effect 0 or close to 0 as compared to is it reasonable away from 0. And in this case, we can simplify our base factor to be just the size of the density of the posterior distribution, given our more complex model, divided by the density value at the certain value of interest theta 0 at the prior. So we're just comparing the size of the posterior density of the more complex model to the size of the prior density of the more complex model. And what we see here is in this equation is that the prior is super important for our base factor because it's one of the two most important parts in this equation. So if we end up using a flatter prior, then the base factor will be different than we're using a more less wider prior. And the influence will be pretty strong, and I'm showing you that in a minute. So the base I'm now already giving you is that base factors without reasonable price are meaningless. So whenever we want to compute base factors, we have to think of price. For other cases, we sometimes don't have to think. We can just use very wide price and it works reasonably okay. For base factors, it don't. Don't use wide price for base factors. So let's take a look. Assume we are again, for this difference, so Cohen's t difference or whatever difference between two groups, let's say for this difference parameter, we are assuming a normal distribution with a mean 0 and standard deviation 0.5. In this plot, we see here the prior, light blue, and the dark blue, the posterior. And based on what we have seen in the second equation, which is called Savage-Dickey ratio, we compare, so this is the size of the prior to the size of the posterior at our value of interest 0. And we see that roughly, when we take a closer look, it's not nicely visualized here, is that the posterior is 3 times less likely than the prior in this case. So the base factor in favor of this is actually wrong direction, the base factor in favor of the alternative model that the effect is not 0 is 3. So we have some evidence that the base factor is actually non-zero. So it's with a base factor of 3, it's some very minor evidence. But then, if we change the prior to a much wider prior, so a normal distribution with mean 0 and a standard deviation of 2 as compared to 0.5, the prior gets flatter. The posterior isn't affected that much, so compare this posterior to this, it's not that hugely different, but the base factor is changed by a factor of 3, roughly. Yeah? So suddenly the base factor is 1, which means basically a posteriori, both models, so the model with 0 effect and the model with a non-zero effect is basically equally likely, which we see that both prior and posterior are roughly equally likely at this value of interest. So even though the posterior hasn't changed much by means of our two priors, the base factor has changed dramatically. So whenever we, going to use base factors, we have to think of priors, and that's hard. So there are many people, thinking about reasonable priors. For base factors and for simple models, we have some reasonable priors, it's still debatable, but that's okay-ish. But for more complex models, like multi-level models and stuff like that, we're still, in the beginning to define reasonable priors for base factors, for multi-level models. So that's an active area of research, and, maybe after we have found some reasonable priors, I can, tell you whether I like base factors in general or not, but currently I'm rather skeptical because in the models that for the models that matter to me, for complex multi-level models, base factors are practically not usable at the moment because we have no reasonable or no good way of defining reasonable price. Okay. So take-home message. price are part of every model. So even in the fragmentist framework, price are part of the model. We just don't realize it. And so their price are unavoidable. And price are good in the sense that they can help us to improve inference considerably by either providing shrinkage, by providing explicit, reasonable prior knowledge, by identifying our model for particular parameters which are not identified by the data and stuff like that. So priors can really help us to improve inference. If we don't want to, have some much prior information and not much experience, that's okay. We can still use wide priors, in which case the Bayesian estimates will not be too far away usually from the classical statistics estimates. That's okay, but we miss one important point or one important possibility to improve our inference by means of price. And we should always make price explicit. So telling what price we use. I mean, we use the default price of whatever package we were using in the version 2.0 or whatever. That's okay-ish if you're not too familiar with price and the internals of the package. But as soon as you're using informative explicit price, you should make them explicit so that people can understand and criticize you for those price. And setting price is hard, and I didn't give you an explanation how to reasonably set price in all cases, because that's hard and it has to be problem specific. But I believe, I'm not sure if you believe this after the talk, that there is no reason to be afraid of price. It's an option, it's a possibility we can use and we should use usually in Bayesian statistics, but we don't have to be afraid of price, or don't have to be afraid of biasing our analysis, or making doing bad stuff with priors in general. So yeah, thanks for listening.